Welcome to Teach Mechanical YouTube channel. Today's topic is fluid statics, right? Uh, Fluid statics. Fluid statics means fluid at rest. We are already at, uh, at, at the rest there is no shear stress. The only force is normal force due to pressure is present. Okay. Pressure is defined as force per unit area. Force per unit area or the amount of force exerted on a unit area of a substance or on surface. This can be stated by the equation P equal to force by area. Okay, force by area for finite area. Okay, if we go for infinite area, P equal to dF by dA, right? Unit for pressure is normally Newton per meter square. This is a SI unit. Other units also available. See that. This is one example. A load 200 pounds. Okay, a load 200 pounds is exerted on a piston confining oil in a circular cylinder with an inside diameter of 2.450 inch. Compute the pressure in the oil of the piston. Okay, what is the pressure formula? Force by area. The formula is available here. See that this is the formula. P equal to force by area. Here the force is this load is the force, right? Force, what is the force here? Given 200 pounds. Okay, 200 pounds. Here 200 pounds divided by area. Here what is the diameter? 2.50 inch. Okay, so you know the area of the formula for the area of cylinder. Cylinder cross section area is circle, so pi by 4 into d square is the area of the circle. Okay, I got area 4.91 inch square. Substitute here 200 pounds divided by 4.91 inch square equal to 40.7. Okay, this is the answer for this problem. Okay, simple concept is load acting on area. Okay, this load is acting on area uniformly, so here the circular cross section area is given, right? Next, principles about pressure. Okay, principle about pressure. What are the principles available and how it's work? What are the derivations are there? These are all things were seen in later slide. Two important principles about the pressure were described by Blaise Pascal. Okay, Blaise Pascal, a 17th century scientist. Okay, Pascal is 17th century scientist. Okay, the pressure act uniformly in all direction on small volume of fluid. Okay, pressure act uniformly in all direction on a small volume of fluid. In fluid confined by solid boundary, pressure act perpendicular to the boundary. Okay, if you go for a solid boundary, pressure act perpendicular to the boundary. Okay, what is the cross section of the boundary? Based on that, it will act perpendicularly, right? Okay, this is the various cross section and how the force will be act in if varies the cross section. Okay, curved shape, how the force is acting, and uh, rectangular or square shape or inclined shape, how the force will reacting. See the diagram, right? This is the next. We go for Pascal's law. Pressure at a point is same in all direction. Okay, it is derived from Pascal law. Is it state that the pressure or intensity of pressure at a point, okay, at a point in a static fluid is equal in all direction, at a point equal to all directions, okay. The pressure acting all the direction will be equal, okay. This is proved as the fluid element is very small dimension, that is dx and ds. This is a fluid element, consider this is a fluid element, okay. Dimensions dx and ds, okay. There is dx is a thickness, right? ds is here. Consider an arbitrary fluid element of wedge shape, okay. This is a wedge shape, this is a wedge shape in a fluid mass at rest as shown in figure. This is a figure 2.1. Let the width of the element perpendicular to the plane of paper is unity and px, okay. Here px perpendicular dimension dy into 1, okay. This is the area, the thickness is 1, this is the area, this is the pressure in x direction, okay. See that py and pz are pressure or intensity of pressure acting on the face ab, bc, AC, BC respectively. Let ABC equal to theta, okay. Let ABC equal to theta. Then the force acting on the element are what are the forces are acting on the wedge element? The first one is a pressure force normal to the surface, okay. Pressure force normal to the surface. Second one, the weight of the element in the vertical direction, okay. These two forces are acting, one is pressure force, another one is a weight, okay. The force on the faces are force on face AB, okay. Go for previous slide. The force on the face AB, this is the AB, okay. Px dy 1, okay. Px dy 1, Px into area of the face AB, this is a Px into area dy into 1. Similarly the face AC, okay. If you go for AC, here the AC is here, okay. Py into dx into 1, right. Py into dx into 1. After that, similarly BC, okay. Pz into ds into, similarly face BC, here where is a BC, this is BC, okay. Here also you have a pressure into area, Pz into ds into 1, right. Then you go for weight of element, okay. Weight of element, mass into gravity. You know the formula for weight, mass into acceleration due to gravity, okay. Go for mass, if you go for mass, density is mass by volume. So here mass, if you want to mass, volume into density, and acceleration due to gravity, okay. This is the weight, okay. Volume into rho into g, okay. You go for volume, is the formula half into bh, so half into ab into ac into h1, okay, into rho g. So density rho is a density of fluid resolving the force in x direction, okay. Resolving the force in x direction. The x direction force, what are the x direction force? This is the x direction force, okay. And here also the inclination take place, you have a horizontal component force and vertical component force. So here px dy 1 minus P into ds1 sin 90 minus theta. Okay, this is the horizontal component force sin 90 degree minus theta, that is cos theta, right? Here px into dy1 pz ds1 cos theta equal to 0. So ds cos theta equal to ab equal to dy. Okay, ds cos theta equal to dy. You substitute ds cos theta as a dy. Here substitute px dy1 minus pz dy1. Okay, what will happen? The dy1 is common. That will be moved to right side here, divided by dy dy1. What will happen? 0 divided by anything got 0. So px equal to pz, px minus pz equal to 0. So px equal to pz. Okay, or similarly resolving the force on y direction, same way py dx1 minus pz ds into 1 cos 90 degree minus theta. Okay, here 90 degree minus theta, here the vertical component force. So here the weight also included, dx into dy divided by 2 into 1 rho g. This is the weight, already we are discussing in previous slide. This is the weight, py into dx minus pz into ds sin theta minus dx dy divided by 2 into rho into g. Okay, equal to 0. But ds sin theta equal to dx. Okay, ds sin theta equal to dx, and also the element is very small and hence weight is negligible. Okay, what will happen here? Ds sin theta equal to dx, here the weight is neglected. Why neglected? Is very small. Okay, the element is very small and hence weight is negligible. Okay, after negligible, py dx minus pz dx. Okay, dx commonly put out and move to right side. What will happen? 0 divided by dx, the total term is 0 here. Okay, 0 divided by dx, here 0 divided by dx. Okay, 0 divided by dx is total term is 0. So by equal to bz. Okay, from equation 2.1 and 2.2, 2.1 is proved that px equal to c, px equal to pz, here px equal to py. So from the equation 2.1 and 2.2, px equal to py equal to pz. Okay, this is a Pascal law. Okay, px equal to py equal to pz. The above equation shows that pressure at any point in xyz direction is equal, since the choice of fluid element was completely arbitrary, which means the pressure at any point is same in all direction. This is proved from Pascal law, right? Next, variation of pressure in static fluid. Variation of pressure in static fluid. Last derivation proved that all the point in static fluid will be same. Okay, this is variation of pressure in static fluid. What will happen if variation of pressure in static fluid? It is proved by hydrostatic law. Okay, it states that the pressure at any point pressure at any point in a fluid at rest is obtained by hydrostatic law. Okay, the pressure at any point in a fluid rest is obtained by hydrostatic law. Okay, which state that the rate of increase of pressure in a vertically downward direction must be equal to specific weight of the fluid. What is the statement here? The state that which states that the rate of increase in pressure in a vertically downward direction, right? The rate of increasing increase of pressure in vertically downward direction must be equal to specific weight of the fluid at that point. Okay, equal to specific weight of the, here see, the specific weight of the fluid at that point. Okay, at that point. This is proved as, consider a small fluid element as shown in figure ABCD. Here A, B, C, D is a small element, right? A small element is area del A is the cross section area of the element, del Z is the height of the element, and P is the pressure on face AB, Z is distance of fluid element from free surfaces. Okay, the force acting on the fluid element. Okay, what are the forces are acting here? See that first one is the pressure force on AB. Okay, this is the AB, this is the AB, the pressure force acting on a AB. Force means pressure into area. Okay, pressure is force by area, so force is pressure into area and acting perpendicular to face of AB. Okay, in downward direction, and pressure force acting on CD. Okay, P plus dou B by dou Z into del Z into dA. Okay, here the force is indicated in a diagram, right? The opposite side pressure force. Okay, and then third one, weight of the element. Weight of the element equal to density into G. Okay, density into G into volume. You substitute here and you got rho G into del A into del Z. After that, fourth one, the pressure force on the surface BC and AD is equal and opposite. Okay, the pressure force on surface BC and AD are equal and opposite. Okay, BC and AD equal and opposite. For equilibrium of fluid element, we have, okay, what are the forces here? This is a pressure force plus this is a downward direction P into del A, this is upward direction minus, and weight also downward direction, this plus, equal to 0. Here you multiple with del A, P del A minus dou B by dou Z del Z del A plus rho G del A del Z, sorry, del A Z equal to 0. Okay, here this value is cancel, P del A cancel, this one is plus, this one is minus, that is cancelled. After that, remaining term minus dou B by dou Z del Z del A plus rho G into del A del Z. Okay, commonly out del A del Z and cancelling, remaining term dou B by dou Z equal to rho G. Okay, rho G, is known as W, specific weight, right? Rho G equal to specific weight. Next, equation 2.4 state that the rate of increase of pressure in vertical direction is equal to weight density of the fluid. Okay, at that point this is hydrostatic law. Okay, what is that? First, the pressure. Okay, pressure, increase in pressure is vertically downward direction is equal to specific weight or weight density of fluid. Okay, is depend on weight density of fluid or specific weight of the fluid. Okay, so here by integrating 2.4, dp, integration of dp equal to rho g dz. Okay, here p equal to rho g z. Okay, here z equal to, that is the pressure gauge. Okay, z is pressure gauge, z equal to p divided by rho g. Here z is called as pressure head. Okay, that's all about hydrostatic law and Pascal law. Thanks for watching. Thank you.